Welcome to our video on Chapter 12, Liquids, Solids, and Intermolecular Forces, presented by Dr. Sylvia Estornson. This video will cover the properties of liquids and solids, intermolecular forces, phase changes, and the unique nature of water. In this video, we compare the gas, liquid, and solid states of matter, focusing on how particle arrangement differs across these phases. This table highlights key differences between solids, liquids, and gases regarding properties like volume, shape, density, and kinetic energy. Here is a summary of different intermolecular forces, including ion-dipole, hydrogen bonding, dipole-dipole, and dispersion forces. This table details the types of solids: molecular, network covalent, ionic, and metallic, along with their structural particles and typical properties. This visual illustrates three types of crystalline solids: atomic solids, ionic solids, and molecular solids. Intermolecular forces are the attractive interactions between molecules. For example, they are responsible for the spherical shape of water droplets. These forces govern everything from how we taste bitterness in coffee to fundamental physiological processes in living organisms. The physical state of matter depends on the balance between intermolecular forces and thermal energy, which stems from molecular motion. In liquids and solids, particles are in close contact, unlike in gases. The key difference lies in the freedom of movement within those phases. This diagram summarizes the states of matter and indicates how adding heat can lead to a plasma state. Recall that gases are characterized by low density, indefinite shape and volume, high compressibility, and weak intermolecular forces. Liquids have high density compared to gases, take the shape of their container, and have a definite volume with moderate intermolecular forces. Solids possess strong intermolecular forces, definite shape and volume, and can exist as either crystalline or amorphous structures. Let's look at the shape of liquids. Because molecules in liquid water are free to move around one another, they flow and easily take the shape of their container. In contrast, consider a solid like ice. Here, molecules are fixed in place, though they still vibrate about those specific fixed points. The most important manifestation of intermolecular forces is the existence of solids and liquids themselves. Without these forces, all matter would be gaseous. Beyond maintaining states of matter, intermolecular forces also lead to phenomena like surface tension and viscosity in liquids. Surface tension is what allows a paperclip to float on water. Gasoline doesn't show this effect because its intermolecular forces are significantly weaker than those of water. This figure explains the origin of surface tension. A molecule at the surface interacts with fewer neighbors than a molecule in the interior. Viscosity is the resistance of a liquid to flow. Substances with stronger intermolecular forces tend to be more viscous because their molecules struggle to move past one another. A common example is maple syrup, which is much more viscous than water due to the strong interactions between its molecules. Vaporization is influenced by surface area, temperature, and the strength of intermolecular forces. Highly evaporative liquids are called volatile, while others are non-volatile. Evaporation is the process where the most energetic molecules at the surface break away into a gaseous state. At any temperature, molecules have a distribution of kinetic energies. Increasing the temperature increases the fraction of molecules with enough energy to escape. Condensation is the reverse of evaporation. When the rates of evaporation and condensation are equal, the system reaches dynamic equilibrium. This diagram illustrates the process of dynamic equilibrium occurring within a closed container. Vapor pressure increases with temperature and decreases with stronger intermolecular forces. Note that it is independent of the liquid's surface area at equilibrium. Finally, boiling occurs when thermal energy allows molecules inside the liquid to turn into gas, forming bubbles that rise to the surface. Let's look at the heating curve of water. As heat is added to liquid water, its temperature increases until it reaches the boiling point, at which point the temperature stays constant until all liquid evaporates. Evaporation is endothermic, meaning it absorbs heat to break intermolecular attractions. Our bodies use this property for cooling. As sweat evaporates from our skin, it absorbs body heat. High humidity, however, makes this process less efficient. Condensation is the exothermic opposite of evaporation, releasing heat as gas returns to a liquid state. This release is why steam burns are so severe, and why coastal regions often experience milder winter nights compared to drier deserts. The heat of vaporization is the energy required to vaporize 1 mole of liquid. For water at its boiling point, this is 40.7 kilojoules per mole. The sign of this value is positive for endothermic vaporization and negative for exothermic condensation. This chart illustrates the specific heats and vaporization data for water, showing the energy transitions between phases. we can use the heat of vaporization as a conversion factor. This allows us to calculate the exact amount of energy needed to vaporize a specific quantity of a liquid, or conversely, how much liquid will vaporize with a given amount of heat. Here is an example calculation. We are given 155 kilojoules of energy and asked to find the mass of water vaporized at its boiling point using the known heat of vaporization. By mapping the conversion from kilojoules to moles and then to grams using the molar mass of water, we find the amount of water vaporized is consistent with our thermodynamic data. When we heat a solid, its particles vibrate faster. At the melting point, the thermal energy is finally sufficient to overcome the intermolecular forces holding the structure in place, allowing it to transition into a liquid. Consider ice melting into water. As long as both phases are present, the temperature of the mixture remains locked at 0 degrees Celsius, regardless of the heat being added. This highlights a key aspect of phase changes: temperature plateaus during melting. The system remains at 0 degrees Celsius until the entire solid mass has transitioned into liquid. This heating curve shows the transition from solid ice to liquid water. Notice the plateau at 0 degrees Celsius during the phase change process. Melting is endothermic, which is why ice effectively cools a drink by absorbing heat from the liquid. Conversely, freezing is exothermic, requiring the refrigeration system to remove the released heat to sustain the process. The heat of fusion is the energy required to melt 1 mole of a solid. For water, this value is 6.02 kilojoules per mole. Like vaporization, this is an endothermic process. Finally, we see the numerical data for the heat of fusion of water, completing our look at the energetics of phase changes. Thank you for watching.